Hi there, my name is Digvijay, and today we will talk about co-simulation in energy systems. In this video, we will define the meaning of co-simulation, explain how it works, and lastly, discuss its use cases. So what is co-simulation? Let us start by looking at an example. Let us consider a local energy system operator, or a LSO, who controls electricity, gas, and heat distribution grids in a community. The LSO asks an electrical engineer to model the electrical grid, a mechanical engineer to model the heat network, and a fluid dynamics engineer to model the gas network. Further, to assess its system, it also asks a control systems engineer to create an advanced machine learning based control strategy. Now, the LSO wants to evaluate how its system will operate. Because the LSO did not specify the modeling framework, the electrical engineer used Power Factory, an incredibly common and sophisticated tool for power systems modeling. The mechanical engineer used Modelica to model the heat distribution network, a tool that is very well suited to modeling such a system. The fluid dynamics guy modeled the gas network in MATLAB, while the control systems engineer developed their control strategy prototype in Python, which is excellent for creating advanced algorithms. The choice of software for modeling the subsystems is obvious. However, this poses the problem for the LSO to now find a way to simulate and assess its combined system. One way could be to ask one of the engineers to convert the models to one software language and then integrate the entire system. This is not such a great idea, obviously. Tremendous expertise is needed to model these subsystems, and the chosen framework, let's say Modelica, may not be best suited to model another subsystem. This is where co-simulation comes into picture. The concept of co-simulation allows users to combine the models developed in different modeling environments. This allows the analysis to retain the developed models in the state-of-the-art software. Because these softwares are mature and state-of-the-art, they have excellent libraries for solving any problems using their own developed solvers, thus accelerating the time and accuracy of the model solutions. Transferring the entire system to a common modeling language can result in making assumptions about certain subsystems, which may not be ideal. The idea behind co-simulation is to simulate various subsystems in a concurrent fashion. This is managed by a central entity called a co-simulation master coordinator. The master coordinator maintains time progression in the simulation, directs the subsystem simulators to stop or start the run of simulators, sets the outputs and inputs from the simulators, and coordinates the flow of information between these simulators. This process can be implemented in two ways: event-based coordination and fixed time step coordination. Event-based coordination, as the name implies, relies on generation of events from simulators and placing them on an execution event list. Here, the main job for the master coordinator is to ensure that events are ordered by increasing time priority and facilitate the provision of data that any simulator may request. A natural question arises: what is an event? An event can be any instance that causes a change in the state of a simulator. Typically, there are three kinds of events a simulator can generate: input event, where the simulator generates an event because it requires an input; a time event, where the simulator has been asked to simulate for a certain amount of time; and a state event, whereby a change in state of the simulator occurs that needs to be notified. Handling an event can alter the list of later events, which is to be managed by the master coordinator. Because the events can occur at non-fixed times, the simulation makes time jumps to the time of the next event in the event list. The second method is to coordinate the co-simulation using a fixed time step approach. In here, the master coordinator lets the individual subsystem simulators run with their own time steps, but at a fixed time interval, queries the simulators to provide information, and exchanges that information with other simulators. At each time step, The MC provides inputs to the subsystems and the next time instance when the subsystems must pause. All this sounds great. However, splitting the system into subsystems comes with its own set of challenges. One of them are co-simulation errors. As we have seen, in a co-simulation setup, the exchange of information between independent simulators does not occur continuously, but at events or after a fixed time interval. This means between this exchange of information, the inputs to the simulators must be interpolated. The interpolation used is either constant, linear, or a polynomial interpolation. Consider this case where the output yt of simulator 1 is to be given as an input to another simulator 2. Since simulator 2 receives input for simulator 1 at only fixed time intervals, it interpolates the received value until a new value is obtained. In this case, it is the constant interpolation. Regardless of the interpolation used, there would be jumps of input at each information time exchange step for simulator 2. These jumps effectively imply a step input to the simulator, which can lead to inaccuracies in the output of the simulator 2. The impact of these jumps can be minimized by reducing the time interval for exchange of information between the simulators. Agonizingly, however, if this time interval is too small, then the simulation time is increased. So it's a trade-off that we must make when setting up the co-simulation. And that is all about co-simulation. Using this technique, we can apply this in several applications towards the energy systems, such as an analysis of coupled electric and heat distribution grids, a transmission and distribution network analysis, and an analysis for coupled gas and electric networks. So let's recap. In this video, you have learned that co-simulation allows us to combine different models so that we can model our energy system properly. This allows us to create models in an extremely detailed way with the possibility of securing our models through encryption. Also, you learned how co-simulation works through its algorithms as well as errors. Through the master coordinator, we can distribute tasks over threads, multiple cores in a machine, or even multiple machines over a single network. Finally, you have seen how use cases of co-simulation can be applied to our energy system. Thank you for watching and see you next time.